Okay, so this would be the second lecture out of chapter 24 and the last lecture. So in this lecture, we'll just look at a little bit of protein, some very basic protein chemistry. Okay, so if you remember, conformation means the spatial arrangement of atoms. And so in this case, we're going to look at the spatial, what proteins look like in 3 dimensions. So the native conformation would be simply the conformation of of the protein in its functional state. So there's basically four levels of protein structure, right? The primary structure, which is, as we'll talk about, is just the sequence of amino acids in the chain. Secondary structure, so we'll look at what are known as alpha helix, beta sheets. Won't say much about tertiary structure, but tertiary structure is basically just the overall 3D shape of the protein. And then quaternary structure is when some proteins are 2 different proteins that are associated with each other, 2 or more proteins, or other things that are associated with the protein, and so that would be its quaternary structure. Okay, so what gives the protein its shape would be non-covalent forces and some covalent forces, but so primarily things like van der Waals forces, hydrogen bonding, ionic bonds, hydrophobic interactions are all going to be at play to give a protein its 3-dimensional shape. Okay, so primary structure is extremely important because primary structure, the sequence of amino acids in the protein, determines the secondary structure, and that determines the tertiary structure and the quaternary structure. So just to illustrate how important the sequence of amino acids are, so the disease sickle cell anemia is a result of one single amino acid residue and hemoglobin being different than what it should be. Osteoarthritis, a single amino acid change in collagen protein causes joint damage, so the sequence of amino acids is extremely important. Right, so the sequence of amino acids, that's the primary structure. That's a unique characteristic of every single protein. It's encoded by DNA, so there's thus genetic information in the sequence of a protein. So this just illustrates one protein and its sequence. So this sequence is that of bovine insulin. So this is the sequence from the N-terminal to the C-terminal end. So this particular protein consists of 2 polypeptide chains, A and B, that are held together by disulfide bonds. So that would be 2 cysteine thiolside chains that have oxidized, and now those 2 sulfurs are bonded together. So chain A is 31 amino acid residues, and chain B is chain A is 21 amino acid residues, and chain B is 30 amino acid. So overall 51 amino acids makes that protein. So proteins can be large or small. Like we just saw with insulin, it's only 51 amino acid residues. So each amino acid in the sequence is called a residue. So just some more terminology to know. So insulin's a small protein, small peptide. It's only 51 amino acids. They can obviously be much larger. Glutamine synthase has 468 residues, so a total mass of molar mass is about 600,000 grams per mole. Connectin protein, molar mass is up to 2.8 million. So they can be very, very large. So this particular protein has a length of about 1,000 nanometers. Okay, so in terms of secondary structure, so we'll look at 3 different classes of secondary structure: what's known as an alpha helix, a beta sheet, and loops and turns. So the alpha helix structure, first proposed in 1951 by Linus and Pauling, Robert Corey. So it's a ubiquitous component of proteins. It's a very, very common feature in proteins. It's stabilized by hydrogen bonds. So this is basically what an alpha helix looks like. So it's basically like a coil. The amino acids part of the protein is in a coil. So there's about 3.6 residues for every turn that this makes, about 3.6 amino acids. So it rises about at 1.5 angstrom per residue. So what holds this alpha helix together, so what's most important to know is just looking at the organic chemistry on it. So what holds it together is the hydrogen bonding. So it's kind of hard to see here, but you can see the yellow lines. The yellow lines are trying to represent the hydrogen bonds. So it's going to be from an NH of an amide bond to a C double bond O from another residue below it in the sequence. So all of the hydrogen bonds in the alpha helix are orientated in the same direction, and so that gives it the protein a bit of a dipole moment. And so that's what these are trying to represent. Those are trying to represent the hydrogen bonds. So you can see an NH there, and hydrogen bonded to a C double bond O. That's below it in the residue. So this is from the N terminal to the C terminal N, is the way that alpha helix is illustrated. So that's a very common feature in proteins. And so in these alpha helices, then they typically have side chains on the outside, outside. So that not very common to have really bulky amino acids on a side chain in the alpha helix, and glycine and proline would destabilize the alpha helices. Okay, so what are beta strands? So first postulated back in 1951. So beta strands can be what are known as parallel or to each other, or anti-parallel to each other. So beta sheets, beta strands, they're just formed by, so you have the peptide chain and another peptide chain that are fairly linear, and they're interacting with each other through hydrogen bonding interactions. So that's what these dotted lines are trying to represent. So that's an NH of an amide bond, right? You can see there's an amide bond there, and that's hydrogen bonded to a C double bond O. It could be in so you have this peptide going along, and maybe it turns and comes back onto itself, and then those strands can hydrogen bond to each other. So they can be in a parallel or an anti-parallel configuration. So here, if you notice, so both strands are going in from the N terminal to the C terminal direction, whereas here you have a strand going from the N terminal to the C terminal in that direction, and this one going from the N terminal to the C terminal in that direction. So that would be an anti-parallel beta sheet. And so in these beta sheets, so this yellow represents the side chains. So you can see there's a side chain up, and then there's a side chain below the beta sheet, then one on top. So they alternate from being bottom to top to bottom. So beta sheets, so each strand's made of about 6 amino acids or so, but again, they're just held together by intramolecular hydrogen bond interactions, and it kind of gives a flat area to the peptide. So loops and turns, so just like it sounds, if you have a peptide chain going along and then it turns back onto itself. So they usually contain, loops usually contain hydrophilic residues, so you may find loops and turns on the surface of protein. And so if it's on the surface of the protein, then that means there's going to be water out here, right? Whereas if it's in the interior of the protein, then it's going to be more hydrophobic environment. So on the surface of the protein, I guess we should draw the protein like this. So that's the surface. So it's on the surface of the protein, then you would tend to have a hydrophilic amino acid side chains out here so that they could hydrogen bond to water molecules. So if the loop only has less than 5 amino acids in the loop, then that's what's called a turn. So beta turns allow the peptide chain to reverse direction. So the carbonyl oxygen of one residue then is hydrogen bonded to an amide proton of a residue three residues away. So that's illustrated here. So that would be the NH, and then if you go 1, 2, 3 amino acids away, then that NH is hydrogen bonded to a C double bond O, and then that's what causes the turn. Okay, so that's secondary structure for proteins, just understanding in general what alpha helices are, what beta sheets are, and what loops and turns are. So in terms of the tertiary structure, so through all of these secondary structures, and that'll give a three-dimensional aspect to the protein, and that's what's known as its tertiary structure. So amino acids that are far apart in sequence can end up being close together, which will allow those side chains to interact, maybe through hydrophobic interactions. So two things that don't like water would tend to be close to each other in space, or if they're very polar side chains, then they can come together and hydrogen bond with each other. Or if they're ionic, if you have like a spartate carboxylic acids carboxylate side chain and a lysine with an ammonium ion. So if you get what I'm saying. So right, if you have a side chain that's carboxylate in nature, and then a side chain like lysine, which is positively charged, then they would like to be near each other because electrostatics would attract. Right, or you may have something like a serine with a hydroxy group, maybe something like the amide side chains, and then they could hydrogen bond to each other. And so that's going to give some organization to the three-dimensional shape of that protein. Or if it's hydrophobic residues, you know, like something like a valine, something like an isoleucine or a leucine, right? They're very hydrophobic in nature, then they were going to tend to aggregate as well. Okay, so proteins with similar primary structure have similar tertiary structure, not surprisingly. So this just illustrates through some examples. So cytochrome C protein from tuna, yeast, and rice, they have similar primary sequence, and if you look at their three-dimensional structure, they're very similar in three-dimensional structure as well. So they're probably going to be able to do similar chemistry. Okay, and then quaternary structure, so we won't say much about it. So quaternary structure just describes subunits in a protein. So, you know, some proteins are composed of two different proteins that are associated with each other, or multiple proteins. So in this case, for example, this will be 4 different proteins that are associated with each other. Okay, so what are the basic functions of proteins? So proteins have many different functions. So it could be structure. So this is just an example. So this is collagen fibers. Or they can function for transport. So hemoglobin and myoglobin are proteins, and so obviously they carry oxygen in the body. Or proteins can function for catalysis. So just to illustrate the catalytic power, so peroxide is very dangerous to a cell. So if there's peroxide in the cell, it must get rid of it very fast. So peroxide can decompose to water and oxygen, 2 water molecules and an oxygen molecule. So if we assign that a rate of 1, so iron trichloride can catalyze this decomposition. So with iron trichloride, the reaction is 1,000 times faster. Hemoglobin can catalyze this reaction, so then it's about 1,000,000 times faster. Or the biological systems have this enzyme called catalase, which can make that reaction 1,000,000 times faster. Right, so enzymes can accelerate reactions as much as 10 to the 20 power over uncatalyzed reaction rates. So there's many different classes of enzymes, what are known as oxoreductases, transferases, hydrolases, and the next slide shows some examples of that: lyases, isomerases, and ligases. So they all catalyze reactions. So what do you think an oxido reductase catalyzes? They would catalyze oxidation reduction reactions like taking ethanol to acetaldehyde. A transferase is going to catalyze the transfer of a group. All right, so they'll catalyze the transfer of functional groups from one molecule to another. Hydrolases, we've seen lots of hydrolysis reactions in organic chemistry. So again, biological chemistry, biochemistry is just really it's just complex organic chemistry reactions that we've covered. So in this case, you have a peptide, so you can hydrolyze peptide bonds to make carboxylic acids and amines, but in biological chemistry, it would be an enzyme that's doing that catalysis. Right? Lyases, we're going to cleave parts of molecules off. In this case, catalyzes the decarboxylation of a molecule. Isomerases, in this case, this malate isomerase will catalyze the isomerization of a cis double bond to a trans double bond, or it could catalyze the opposite, trans back to cis. And then ligases, in this case, right, so ligases will catalyze the reaction between two different molecules. So basically doing the opposite of what a ligase did. So bringing these back together to make bonds instead of break bonds. Okay, so lastly, in this lecture, we'll just look at a few of the basic reactions of amino acids and how do you make amino acids. So we've seen several ways already this semester. So we covered this in carboxylic acid chapter. If you take a carboxylic acid PBr3 Br2, that'll add a bromine here and a bromine there. All right, it's a Halvord-Zielinski reaction. And then water would take this bromine that was added there and knock it back off to give you the alpha halogenated carboxylic acid. And then if you react that with ammonia, this can do an SN2 reaction, and now you have the amino acid alanine in this case. So starting with propanoic acid, or you can make this amino acid alanine through that sequence of reactions. Or this is a reaction you would be familiar with. So if you take an aldehyde and amine, that would make an imine, right? And then once you have the imine, then Cn minus can react with this. So Cn goes here, and then these electrons on the nitrogen to pick up a hydrogen. And now you have this. And then we've seen that you can take the cyanyl group and you can hydrolyze it to a carboxylic acid, right? So that's what's known as a Strecker synthesis. So this reaction looks a bit exotic. So we've seen this molecule before, phthalimide. So we've seen that back in chapter 19. So this base will deprotonate this. And then this will do an SN2 here to knock off the bromine. And now you have that. So it's like a Gabriel synthesis. And then once you have this, so there's still an acidic hydrogen here now. So this would be like a reaction out of chapter 22. So you could take that hydrogen off to make an enolate there. Right, and then that can react here to do an SN2. And then you can do hydrolysis and decarboxylation. All right, so at that point you would have that. So now you do hydrolysis. And so that's going to, hydrolysis then is going to, so if you remember back in the Gabriel synthesis, it's going to open that up. And then it's going to cleave both of these to carboxylic acids. And then one of these is going to decarboxylate and lose Cl2. So then what you would end up with is basically this. Right? So you get that amino acid. And so whatever the R group is here, so any of those 20 amino acids, put that R group there, and then conceivably you could synthesize the amino acid that way. Or this one, so this one's similar. If you react this with ammonia, then you can form that imine. And then if you do hydrogenation, oops, so you get that H and H across the carbon-nitrogen double bond. Right, and then you would have the amino acid. So that's a reaction covered back in chapter 19. So that's what's known as reductive amination. Okay, so that's some ways to synthesize amino acids. So just look at a couple reactions amino acids undergo. So if you take an amino acid and react it with this molecule called anhydrin, then basically what happens is this gets converted to an aldehyde. So whatever the amino acid is, this nitrogen basically ends up between two of these molecules, and you make that, which is called Rumen's purple, and then you lose a CO2 molecule in the process. So the significance of this reaction, this is how you do fingerprint analysis. So if you touch anything, then there will be a little bit of amino acids transferred, and those amino acids will react with anhydrin, and then that'll leave and then you'll get this purple color from Rumen's purple, and so now you have a trace of the fingerprint, right? So sometimes if you ever watch crime shows, you maybe see them spraying a bottle. That bottle would have an anhydrin in it, and that's going to react with any amino acids on the surface of whatever somebody has touched, and then they can lift the fingerprints off that way. So this just goes through the mechanism, how that anhydrin works. If you want to look through the mechanism, not going to expect you to know it. So one more reaction that we'll look at, well actually a couple more. So if you have a peptide, then if you want to utilize that peptide for some purpose, or know what that peptide is or protein is, then you have to figure out a way to get its structure. And as you can imagine, getting the structure of a protein or peptide is not easy, because there are lots and lots and lots of hydrogens. So if you wanted to do spectroscopy, proton NMR spectroscopy, for example, it's going to be very complex NMR if you have 50 amino acids or 100 amino acids or 1,000 amino acids in the structure. That's a lot of hydrogen, so that's a lot of signals, so the spectra would be very convoluted. So there are methods of figuring out the sequence of amino acids in a protein. So this would be one method called Edmond degradation. So you react it with this molecule called phenylisothiocyanate. So basically what happens is nitrogen reacts here, and those electrons go there, and then you lose a proton from here, and that proton picks up one, so you make this. And then if you treat that with acid, then basically what will happen is you'll end up cleaving that off, and this ends up looking like that. The next slide shows a mechanism how that happens, but I'm not going to expect you to know the mechanism. So, but the point is, you've cleaved off one amino acid residue. So now the protein that you have is minus one amino acid residue. And then what you can do is you can analyze this. So if there's only 20 common amino acids, then that's just 20 different possible molecules that could have cleaved off. Although there are other amino acids than those 20, but there's 20 that are very common. But the point is, this molecule has a mass, right? You can analyze what came off using a mass spectrometer, for example, and based on what the R group is, it's going to have a specific mass, that molecule would. And so if you couple this, hook this up to all robotics, and when you go through one sequence, funnel this off to a mass spectrometer and get the mass on it, then you know what what came off of the molecule, and then basically repeat. So you can put this through another sequence of Edmond degradation and chop off the next amino acid, and then do it again and chop off the next amino acid. So you can do this about 50 times before there's some side reactions that start happening in other places in the peptide chain. So after a while, it gets too difficult and too messy to analyze the mixture. But you can do this for about 50 amino acid residues. So this is what's called sequencing protein, figuring out what sequence of amino acids are in the protein. So this just shows you the mechanism for an Edmond degradation. So I'm not going to expect to know that. You to know that, you can look through it if you're curious to know how that reaction happens. Okay, and then lastly, there's other ways to cleave proteins. One way is to use enzymes to do it. So there's an enzyme called trypsin that from the C-terminal end, so that will cleave at lysine and arginine residues. Or chymotrypsin, which will cleave at phenylalanine, so the aromatic amino acids. It'll cleave proteins wherever there's a phenylalanine or a tryptophan or a tyrosine residue. So just to illustrate the process, so if you had this protein and you wanted to figure out what the sequence of amino acids was in the protein, then one thing you could do is you could take that and react it with trypsin, and that trypsin is going to cleave it here, and it's going to cleave it here at arginine and tryptophan residues from the C-terminal end. So now you have 3 fragments. So you've chopped the protein up into smaller pieces, and so now you can maybe do Edmond degradation on these fragments, for example. And this protein is small, you could do an Edmond degradation on that protein by itself without doing this. But if we're talking about a protein that's 100 or 1,000 amino acids in sequence, then you can chop it up into smaller pieces and then do an Edmond degradation on those sequences. So basically then you figure out what the sequences of the smaller pieces are. Okay, so now go back to the same peptide and use chymotrypsin instead and cleave it at different spots. So here you're going to cleave from the C-terminal end by the aromatic residues, so tryptophan and phenylalanine. So now you've cleaved it again into 3 pieces. So now you use an Edmond degradation, for example, and figure out what those 3 pieces are. And then you line these pieces up and you figure out, okay, these are in common. So this alanine must, so from here, if we're just looking at these 3 pieces only, well, you don't know how those 3 pieces go back together, right? Because this could have been attached to there. So was this tryptophan attached to arginine, or was this tryptophan attached to lysine? So you don't know that, but if you put these pieces together, then you know that, because you know that tryptophan must be attached to lysine from this chymotrypsin degradation, and so then you know from that this alanine must be attached to this arginine, and you know that this phenylalanine must be attached to glycine from putting the pieces from the different degradations together. So hopefully that makes sense how that works. So this is one very important area of chemistry and biochemistry and protein chemistry, is if you have a protein and protein does something interesting, you want to figure out what the structure of that protein is, and figuring out the structure of the protein starts with figuring out what the sequence of amino acids is. And then once you have the sequence, then the next biggest task is to figure out the secondary and tertiary structure in that protein, and then figure out what the 3-dimensional shape of that protein is, what its tertiary and quaternary structure is. Okay, so lastly, in terms of purifying amino acids or purifying proteins, one thing that you can do is what's called electrophoresis. So basically the way that this works is you have a gel that you put the amino acids or proteins in, and at one end you have an anode set up, and at the other end you have a cathode set up. So if we put an amino acid like alanine in here, well, alanine is neutral, right? At pH of 7, it has no charge, so it's not going to migrate. So once you hook this up, turn the power supply on, that generates a positive and a negative charge at the opposite ends. Alanine's not going to migrate. So if you had a mixture of all 3 of these, and you put that into electrophoresis, so alanine's not going to move, so you put it in the middle, alanine's not going to move. Aspartate has a net -1 charge, so it's going to migrate towards the anode, which is positively charged. And if you put lysine in there, it's got a net +1 charge. at pH of 7. So it's going to move to the cathode, which is negative charged, and now you've separated the 3 amino acids. Or you could do the same for a protein or peptide. If the protein had a net charge on it, then it's going to move in electrophoresis either to the anode or to the cathode, depending on where the protein has a net positive or a net negative charge. And how do you know whether the protein is going to have a net positive or a net negative? Well, if you knew the sequence, for example, and you knew how many each amino acid and what its pH state is at a certain pH, then you could figure out what the charge on that protein is, and you would know, is it going to migrate to a positive or a negative electrode, for example. Okay, so anyway, that's it for this chapter. So what's the most important things to know? Maybe if you were given a sequence like this, how could you put those back together to figure out the actual sequence of the peptide? Yeah, knowing the different reactions of how to synthesize amino acids. And basically just understanding what secondary structure is, what alpha helices are, what beta sheets are, what turns are, and those intermolecular hydrogen bonding interactions. That's the main thing to understand from this lecture. And then the basic terminology, what does sequence mean? What does primary, secondary, tertiary, and quaternary structure mean? And then that's about it. Okay, so we'll stop there.